This is Dr. Mark Scheuer, Chief Medical Officer at Persist. This video continues the tutorial Anatomy of an FFT Spectrogram. As mentioned before, different color schemes can be used to represent the Zaxis scale. Here I've changed the color scheme from an RGB to a yellow-orange-red scale. This scale uses much more psychophysiologically meaningful color increments to represent the height on the z-axis. In this depiction, the z-axis scale is linear, expressed as microvolts per hertz. Other options are possible. Engineers frequently represent the z-axis of an FFT spectrogram as power in microvolts squared per hertz, rather than as an amplitude parameter. The power spectrogram is created by simply squaring the linear value we've been using in the prior graphs. Using power scaling of an EEG's FFT during trend review is often problematic for two reasons. First, it does not jibe with the electroencephalographer's visual gestalt of the frequency makeup of the EEG. The EEGer doesn't think in the expanded scale of a microvolt squared representation when considering the relative frequency mix of various EEG patterns. The second problem is that, for any given minimum and maximum values chosen for the z-axis scale, a power microvolt squared scale reduces the dynamic range of EEG activity that can be clearly rendered on the graph. This is easily demonstrated in this example. Here the z-axis scaling is changed to microvolts squared, and the upper end of the scale is proportionately corrected for that change, here from 3 microvolts per hertz to 9 microvolts squared per hertz. Although the photic driving responses are still clearly evident and some occupy the upper end of the color scale, almost all other EEG activity has washed away because it's too small to be seen using the microvolt squared scaling. So, although it can be used, the microvolt squared option for scaling the z-axis doesn't seem to be the best choice. Another option, though, going in the opposite direction, often provides a better dynamic range for depicting the EEG's activity. This is a square root scale, which is obtained simply by taking the square root of the linear z-axis values. As shown here, this allows better painting of the full range of EEG activity. Not only are the photic driving responses well visualized, but the harmonics are a bit better evident, and the patient's resting alpha activity is also more obvious. Using the yellow, orange, red color scale, here are the 3 options for z-axis scaling shown side by side. The microvolts squared scale is shown on top, the microvolt scale next, and the square root microvolt scale on the bottom. For most clinical work, I prefer the bottom square root scaling because it imparts more dynamic range to the depiction of EEG activity, and it jibes better with my visual impression of the raw EEG. All of these parameters can be adjusted after the fact, as desired. However, by using the square root scale, I find that I only rarely need to make adjustments to the z-axis scaling. Now let's return to the original clinical example and examine it in detail. These spectrograms show a frequency range of 0 to 20 Hz on their y-axes. Their z-axes use an RGB color scale in the square root representation. The graphs represent averages of the FFT spectra obtained from multiple bipolar channels in the left and right hemispheres, respectively. Hemispheric averages are often a useful simplified representation of the EEG because most significant EEG changes involve at least a few channels in a hemisphere. Graphs that show hemispheric averages are usually good at depicting significant changes, while still allowing assessment for hemispheric asymmetries. These graphs also incorporate Persist's adaptive artifact rejection, which helps clear the trends of noise created by electrode artifacts, but that's a topic for another session. There are 5 instances of major changes present in the right hemisphere spectrogram, along with smaller, slightly lagging changes on the left. To demonstrate the correlation between the spectrogram changes and the EEG, I'll switch to a 30-minute view of the trends and split the magic marker page to show time-synchronized EEG. This is a display configuration that's similar to one I typically use during review of a prolonged EEG. This view adds a seizure probability graph above the FFT spectrograms, but it's otherwise configured identically to the graphs just presented. Based on the spectrograms, let's predict what the EEG will show during the time period just following the vertical blue line in the trend window. The first substantial spectral change is a sudden increase in amplitude of right hemispheric activity at a frequency of about 15 Hz. Activity that's still increased in amplitude compared to baseline then progressively shifts from the beta range to the alpha range to the theta range over the course of about 60 seconds and ends in heightened delta activity. Late in the event, a left hemispheric change also appears and consists primarily of higher amplitude delta activity. Now let's page through the EEG to see just what happened. By clicking on a spot in the trends just before one of the major changes, I can select this time as a starting point and then page forward through the EEG. The vertical blue cursor line in the trends will synchronously advance as the EEG pages forward. As seen on the EEG, a seizure begins with rhythmic beta activity in the right frontal region. This progressively slows and shows some spread on the right. The seizure concludes with rhythmic delta activity that's maximal on the right, but also present on the left. The spectrogram changes accompanying each of this patient's seizures are quite similar. This makes it easy to identify the 3 seizures that occurred during this half hour of monitoring. Stereotyped trending patterns are usually present during a particular patient's seizures, and once recognized, these similar patterns make identification of most subsequent seizures a quick task. Relatively stereotyped ictal trending patterns occur because a particular patient's ictal EEG patterns usually bear strong similarities from one seizure to another. These features make the FFT spectrogram a useful tool for seizure hunting during review of lengthy EEG recordings. The FFT spectrogram's ability to clearly depict EEG frequency changes also makes it a useful tool for assessing asymmetries of slow or fast patterns, as are often present during cerebral ischemia. In another session, I'll review the anatomy of an asymmetry spectrogram, a tool that makes recognizing focal asymmetries an easier task. I hope you've enjoyed this video tutorial on anatomy of an FFT spectrogram. Thanks for watching.